today we'll again start by finishing off this part about the power of periodic signals. Periodic signals are mostly power signals because the energy is finite on a period and is some finite positive number on a period, and since the signal repeats itself an infinite number of times, so the total energy is typically infinity. So they are typically power signals, and you can compute their power by compute the energy on a period, okay, and then you divide by the period, which is big T in the case of continuous time periodic signals, and big N in the case of discrete time periodic signals. Okay, so let's show that this is true. So remember that, for example, in the continuous time case, the formula for the power is that you take magnitude x of t squared, you integrate from minus L to L, you divide by 2L, which is basically the length of the domain of integration, and then you take the limit as L goes to infinity. So we need to show that basically this guy can lead to this case here if the signal is periodic. And here is the idea. The idea is the squeeze theorem. You want to compute the integral, and from minus L to L, so let's focus on 0 to L. So you are integrating the signal from 0 to L. So what you can do is that you can divide your integration into periods, right? So this is 0 to t, and then 2t, and then 3t, and so on and so forth. Okay, so you can think of the domain of integration being divided into periods, and on the other side, like from minus t to 0 and so on. And then you can upper bound your integral, right? So basically, how many periods do we have? Let's say from 0 to L. How many periods do we have? We have L over big T periods from 0 to L. L divided by T. So what you can do is that you can, as an upper bound, you can take L divided by T. Okay, this may be, this number maybe like, let's say 100, 100.5. So basically we have 100, complete periods and then half a period. So what you can do is that you can basically take the ceiling of this. So if it's 100.5, you say that it is 101. Okay, so you take L over T, then you take its ceiling, and then you multiply by T. So this thing here is greater than or equal to L. And as a lower bound, what you do is that you take L over T, but now you take the floor, okay, and then you multiply by T, and so this thing here will be less than or equal to L. Okay, so that's the idea. Is basically you can find an upper bound. You can find an upper bound by using the ceiling, lower bound by using the floor, and now you are integrating from, if you divide this integral into two integrals, from 0 to this number. This is an integer number of periods, right? Because now the advantage of using the ceiling or the floor is that those guys are integers. So now we have a complete periods. Okay, so now we are integrating over complete periods. While if we just integrate to L, for a general L, again, if you divide L by big T, you may get a fraction. But by doing the ceiling and the floor, you basically get integers, and now you are doing the integrals over complete periods. And now, because the signal is periodic, so if it's periodic, then basically the integral over a number of periods is basically the number of those periods multiplied by the integration over just one period. Okay, so that's basically the idea here, is that you do this upper bounding and this lower bounding. Okay, and then basically you divide by 2L to match the definition of power. So that's the power of a continuous time signal, and you can do the same for a discrete time signal. And then you basically compute those limits, the one with the floor and the one with the ceiling, and you will find that the limit is exactly the same. So by the sandwich or squeeze theorem, basically the power, basically the limit of the power exists and is equal to basically this expression here. And again, it's the same story for discrete time signals. So let's go here. So again, the trick is by doing this upper bounding and using the ceiling. Now, how many periods do we have inside for this integration? So we have 2 multiplied by this integer number of periods, which is the ceiling of L over T. Okay, so what we can do is that we can take the the integration over 1 period. Okay, so this guy, you take the integration over 1 period. Okay, and then you multiply by the number of periods. So this is 2, and then basically you have the CL of L over T. So this is the number of periods that exist now on the domain of integration, and you have 1 over 2L there. Okay, 2 goes with 2. 2 goes with 2, and then what you can do here is that you can multiply by big T and you divide by big T. Okay, so so what you will get is basically 1 over T multiplied by the integration over just 1 period, which is basically the formula that we want to prove. And then there are extra terms here. The limit as L goes to infinity of L over T, the ceiling, multiplied by T over L. On the other side, things are the same, except that rather than having the ceiling, we have the floor. Okay, and so so it's like we need to show that basically the limit of this thing here and the limit of that thing here, both limits are equal to 1. And if we do so, then we are done. Okay, so how can we show, for example, I will just do one of them. So how is this limit equal to 1? The floor function, a floor L over big T, multiplied by T over big L, and then you are taking the limit as big L goes to infinity. So what is the meaning of the floor? The floor of L over T, so that's a real number, is less than or equal to L over T, and is bigger than L over T minus 1. So generally, the floor of some real number alpha is less than or equal to alpha, right? It's equal to alpha if alpha is an integer. If alpha is an integer, then its floor is basically itself. And the floor is always strictly greater than alpha minus 1. Okay, again, because you take alpha to the nearest lower integers. Okay, so if this is a number, so if this is alpha, then floor of alpha is basically the highest integer that is, the highest integer that is less than alpha. The distance between alpha and the floor of alpha basically is always less than 1. If alpha is an integer, then the floor is basically equal to alpha itself. So using this inequality for the floor, we can write that the floor of L over T, again, it's upper bounded by L over T, but it's lower bounded by L over T minus 1. And then you multiply by T over L, which we have here and there. So this is the T over L. And so now the upper bound becomes 1. And if you take the limit as L goes to infinity, that's the constant sequence of 1s. So its limit is 1. And then for this guy, as you take the, for a given T, big T, if you take the limit as L goes to infinity, T over L will go to 0, and 1 minus 0 will be 1. So the limit both on the left and right will be exactly equal to 1. And so here we get 1, here we get 1. And so the power is basically given by this expression here. Okay, so if you have a periodic signal and it's a power signal, which is typically the case, then again, rather than taking limits, what you can do is just you can obtain the energy over a period, and then you can divide by the period, and the same is true for the discrete time signals. Okay. Now, in many applications, we have like a sort of a finite sum of sinusoidal signals. And what is the power of this finite sum of sinusoidal signals? Note the following: that once you add sinusoidal signals, then there is no guarantee that basically the sum itself is a periodic signal. Okay, so remember this rule that if you add two sinusoidal signals, then if the ratio of their periods is an irrational number, then actually the sum is not periodic, and so on. Okay, so that's the reason here. Like if you sum a number of sinusoids and you want to find the total, the average power of the sum, then it is better actually to use the limit. To use the limit formula, the original formula, the original definition of power. Again, I cannot basically say that I will integrate over a period and divide by the period, because maybe actually if two frequencies, the ratio is an irrational number, then actually we don't even have a periodic signal. Okay, so we have a sum here, and again we are back to using the limit formula for the average power, again because the sum in the trivial case in which you just have one component, one sinusoidal component, it is guaranteed to be periodic, but two or more, it depends. If the ratios, if the pairwise ratio of any frequency, of any two frequencies is a rational number, then yes, then basically the sum will be a period. But we will not basically care about this. So here we have n components. Each one has its own complex magnitude, and those are the complex exponential, and they have frequencies, and we will assume that those n frequencies are different numbers, okay, are different. So f1, is, no two frequencies are equal in this. Okay, so definition of average power, again, using the original limit expression, because maybe the sum actually is not periodic, is that we will, again, take magnitude x of t squared, integrate from minus L to L dt, and then we scale by 1 over 2L, take the limit as L goes to infinity. So now x of t itself is a summation. It's a sum of, those n complex sinusoids, each with its amplitude, and most importantly, each has a different frequency. Now, what is basically the magnitude square of this summation here? So the sum, it's the magnitude square of a complex quantity is like you take the complex quantity and you multiply it by its complex conjugate, right? So this is like a1 e to the I 2 pi f1t plus a2 e to the I 2 pi f2t and so forth. Okay, so this is basically the first bracket. It's a summation, and then you multiply by its complex conjugate so that you compute the magnitude square. So this will be a1 conjugate, because we assume the amplitudes are generally complex. And then you have e, this I becomes minus I 2 pi f1t plus a2 conjugate e to the minus I 2 pi f2t, and so on. So basically, we will have two brackets, each bracket having n terms, and so when we multiply them together, we will have n squared terms. Okay, and so we can write basically the magnitude squared of a summation as a double sum. A double sum. We have n squared terms, and then we have basically k from 1 to n, j from 1 to n, akaj conjugate, and then e to the I 2 pi fk minus fgt. Again, because we multiply one bracket multiplied by its complex conjugate. So one amplitude here will appear with the conjugate sign, and one frequency will appear with the minus sign, because when you conjugate this I, it becomes minus I. Okay, and so this is basically the magnitude squared. It is the sum multiplied by its complex conjugate. Now those sums here are finite sums. Okay. So integrals are basically linear, okay, and so which exactly means that if you are integrating a finite sum, then you can simply do the integral of each term on its own, and then you sum the results, and you do not need to justify this. I mean, this follows from the linearity of integration. Now, we'll take this for granted. Of course, proving the linearity of integration may not be that straightforward. You need to prove it from the definition of the integral, and it will depend whether your integration is Riemann integration or Lebesgue integration. But the idea is that we'll take this for granted, that integrals are linear in the sense that if you are integrating a finite sum, you can you don't even need to say it. You can just bring this integration inside, and focus on basically this part that contains the time variable t. But if the sum is an infinite sum, then that's when you need something like Tonelli or Fubini or something. Okay. So we will basically move the integration inside and integrate the function with respect to t, and this function, well, so we have two, if these two indices. Each one of them runs from 1 to n, and then we have two cases. So there is the case k equals n, and so k equals n equals 1, k equals n equals, j, k equals j, k equals j equals 1, k equals j equals 2, k equals j equals 3, and so on. So these are when the two indices are the same, and when the two indices are the same, these two guys are the same, fk minus fk, f7 minus f7, and so e to the 0 is 1, and the integral will give you 2L. The integral will give 2L when the two indices are the same. And this happens for how many terms? N terms. So there are n terms in the double sum in which the two indices are equal to one another, For basically for this case in which the two indices are equal, basically the integral is exactly equal to 2L. Now there are n squared minus n terms in which the remaining terms, I mean, in which k is not equal to j. And in that case, these two frequencies are different because of our assumption that basically the frequencies are different from one another. And so the frequencies will be different, and because it's a simple integration. It's an integration of an exponential function. So you do this integration, and so you bring this guy here. Sorry, everything here multiplied by t will come in the denominator, and we don't fear like dividing by 0 because we know that when k is not equal to j, so k not equal to j, we know that basically these two guys, their difference is non-zero, and so we are not dividing by 0, so no trouble, nothing here. And then you have a sign over something, and we express it in terms of the sinc function. Okay, so if you don't know the sinc function, it will come later in this lecture. Okay, and so we'll, because there are like two definitions for the sinc, and we need like to agree upon like the definition that is used in this course. So it will come. Okay, it will come. Let's not like get ahead of ourselves. This so this sign over sine 2 pi fk minus fjl divided by this thing will be the sinc, and the argument, if the argument of the sinc continuous function. We didn't show convergence of the limit. Basically the limit here, we are doing things with respect to the limit. We are doing things in the correct order. So we are computing everything here, and then finally we will take the limit. Now the limit also be exchanged with the finite sum, because the limit is also linear. Okay, so if you have a limit applied to a finite sum, or an integral applied to finite sum, or a differential operator applied to finite sum, again, those operators or operations are linear, and so you can simply interchange. I can take this limit and bring it inside. Nothing is required, just the linearity of the operation of a limit, or to get this integral inside the linearity of integration. Okay, so this again because our sum here are finite, and I am obeying the order. Basically, I am doing the sums and integrals, and then finally I am taking the limit. Okay, you need to justify again if one or two, or basically both of those sums are infinite, then you will need to basically you start using basically Fubini or Tonelli for interchanging the order of integration and summation, and infinite summation if it's infinite summation. Now for the limit we do not need justification again, because we are actually doing things or I am not moving the limit inside or anything. It's like you evaluate this thing, and once you evaluate this thing, you will get a function, basically this thing here, with finite sum. Okay, so again, you don't need like the DCT, the dominated convergence theorem. You can just take the limit inside, and because the number of the terms here are finite, and you apply it to the integral, but actually after evaluating the integral. So I'm not like taking the limit inside. I'm actually evaluating the integral and then taking the limit. And the sinc function, we will see it later. Basically, it decays. It's a continuous function. It is a continuous function on R. Okay, and it decays to 0 when its argument goes to plus or minus infinity. Okay, so we have an L here. So as the argument of the sinc function gets larger and larger and larger, basically this sinc goes to 0. This limit is 0, and so the double sum where basically the two indices are different, this will give you exactly 0, and you are left with only the first case. So when the two indices are the same, basically this integral will give you 2L. 2L divided by 2L, that's 1. That's 1, okay? And when the two indices are the same, AK multiplied by AJ, now J is equal to K, so it will be AK multiplied by AK conjugate, and so this will give you magnitude AK squared. And this will be the surviving term, because the limit will give you 0. Okay, so so if you want the power of this summation here, if the frequencies are all different from one another, what you need to do is just take those guys, and take their magnitude squares, sum the magnitude squares, and you are done. This will be the average power. Okay, if your sinusoids are discrete time, then the same rule applies, and you will prove it in homework 3. So it's sort of the same thing. It's only that the definition of power is different. Like for discrete time signals, the definition of power will be like a summation from minus big M to big M, and then you divide by 2 big M plus 1, and then you take the limit. So it's like, the difference will be that, like, you have it, this guy will be replaced by this integral here will be replaced by a summation, but in essence you will get sort of the same steps that you see here. Okay, so let's solve an example. So suppose as a special linear operation. I mean, what is exactly the linear operation? Sum of squares? No. I mean, no, I do not. I don't understand. So basically,
yeah, my question is, usually when you put square on any function, you have extra terms, so you can't do superposition. But here we concluded that the power is only containing the terms themselves. Like, we don't have extra terms when you square.
So basically, I mean, what happened here is that there are cross terms here. So there are cross terms, but it turns out, that they are multiplied by zeros. So, I didn't so basically we obtained this result. Yeah, I mean, under the assumption that, the frequencies are different from one another, you can show that basically the cross terms, we didn't ignore them from the beginning. They are there, but it turns out that all of them are simply, for every k not equal to j, basically you have sync of something positive multiplied by L, and as we will see later in the lecture, basically when L goes to infinity, this sync will go to 0, and so all those cross guys will disappear, and you have this summation here. It's sometimes called like incoherent sum. Some people call it incoherent sum, in which like you have a sum of signals, and by power you basically take the power in each single component and add the powers. So sometimes it's called incoherent sum. For coherent sum, typically people mean something like this. Say you sum and then you take the magnitude squared, and in this case, yes, you will get basically cross terms. But in our case here again, and it's important, and you'll see in the example that those frequencies are different, which means that if you want to avoid the cross terms and enjoy this final result here, you need first to collect the sinusoidal components with the exact same frequency before you apply this formula. So what do I mean? So this is an example. You are required to compute the average power of this signal. So it is 2 cosine 2 pi t, 7e to the I 2 pi t, and then 4e to the I 2 pi minus 40. Okay, so to match basically the proof or the derivation, it's better that you take every sinusoidal signal and use Euler's formula to write things in terms of complex exponentials, right? So if you find the cosine, then cosine theta is e to the I theta plus e to the minus I theta over 2. If you find sine theta, then it is e to the I theta minus e to the minus I theta over 2i. Okay, so you convert everything into complex sinusoids, complex exponentials like this. So 2 cosine 2 pi t, it's e to the I 2 pi t, e to the I minus I 2 pi minus 1t. So this is the 2 cosine. And then we have these two terms are already in the form of complex exponentials. Then, very important, because if you don't do this, then actually this proof will fail and you will actually have cross terms. So you find that there are complex sinusoids with the same frequency. Let me change the color. So this one here, the frequency is 1 hertz, so it's e to, remember this is the general formula for a complex exponential. So here we have this guy with a frequency 1 hertz, and this guy also has the same frequency 1 hertz. So you need to take these two guys and combine them together. Okay, the other guys, they have different frequencies. Okay, so one of them, the frequency is minus 1 hertz, and in the previous lecture we talked about the negative frequencies, and here we have minus 4. once you put your stuff in this formula here, then of course you do not need to reinvent the wheel. The power will automatically be the magnitude squared of this guy plus the magnitude squared of 1 here plus the magnitude squared of 4, and you compute it whatever you get, and this will be the average power of the sum. Okay, so again, like what you can do if you find a sum of sinusoids, perhaps a mixture of sines and cosines and complex exponentials, what you can do is that apply Euler, convert everything into complex exponentials, combine the exponentials that have the exact same frequency, and note that the frequency minus 1 hertz is different from the frequency 1 hertz, and so on and so forth. So negative frequencies in complex exponentials, they are different animals, okay? So this guy here, it's alone. I mean, this minus 1 is, you know, different from these two guys, but these two guys, they have the same frequency, so they should be combined together. Once you get a sum of complex exponentials, each with its own different frequency, then you just take the you know, those guys, take the magnitude squares, and you sum, and this will be your average power. Okay. We can classify signals. So we talked about periodic versus aperiodic. We talked about energy and power signals, or signals that are neither. Also, we can think of signals in terms of symmetry. They can be even, odd, or neither. And even signals are basically signals satisfying for the continuous time case, x of minus t is equal to x of t for every t. And those are signals that if you plot, you will find that basically they look the same. You know, if you look here or you look there. The same can be defined for sequences. So those are the even. The odd ones, they define x of minus t is equal to minus x of t. So a signal, for example, if it looks like this, for positive t, if your signal is odd, then it should look like this for negative t. So that's an odd signal. And the same for sequences. You can define this, you know, if x of minus n is equal to minus x of n for every integer n, then it is an odd signal. Of course, you know, not all signals, in fact, the overwhelming majority of signals, they do not have such a symmetry, and so most signals are actually neither even nor odd. So it's like power and energy. So it's not like two clauses. Actually, we have three clauses: even, or odd, or neither even nor odd. Okay. For odd signals, it's nice to keep in mind that the value of the signal at 0 should be 0. And how do you see this? Basically, put here 0 in either one of these forms, whether we are talking about continuous time or discrete time signal. So x put t equals 0. What is x of minus 0? It is x of 0. Minus 0 is just 0. Okay. And according to the definition of an odd signal, this should be minus x of t or n, which is 0. And so this is an equation to x of 0 is equal to 0, and so x of 0 is equal to 0. Okay, so for always keep this in mind that x of 0 is equal to 0, and this is true if we are talking about a continuous time signal. So for an odd signal, basically going through this origin here is not like an accident. It must be the case that you go through 0, and the same if we are talking about sequences or discrete time signals. Now, if you have a general signal, you can write it in terms of an even part and odd part, okay? And so those parts will, you know, even and odd, you know, they will be useful like in Fourier analysis. So we'll study, for example, what if you take the Fourier transform of an even signal, an odd signal, an even real valued signal, and so on. So this will come. But, you know, just for now, keep in mind that any arbitrary signal can be written as a sum of two signals. Okay, and I'm doing this here for continuous time signals. The same is applicable to discrete time signals. I can write x of t as an even signal plus an odd signal. An even signal plus an odd signal. And so the question now is, what are these two signals? The trick is to take x of t and replace t by minus t. Okay, so if you replace t by minus, so again, we are assuming that this is valid for every t in R. So we can replace t by minus t. And when you do so, you get x of minus t, xe of minus t, xo of minus t. Now, by definition, we are trying to take x of t and express it in terms of this xe of t, which is an even part. So it's an even signal. So xe of minus t by definition is equal to xe of t because it's an even signal. Now, xo of minus t, because this is desired to be an odd signal, then xo of minus t is minus xo of t. So now we have two equations. X of t is equal to x even t plus x of t. This is what is desired. We want to do this decomposition and take an arbitrary signal and write it as the sum of two signals with symmetry properties. One of them is even and the other is odd. X of minus t, because of the symmetry, will be xe of t minus x0 of t. And now you can see that basically if you add these two guys, then the x odd will disappear, and if you subtract, x even will disappear. Okay, so the sum x of t, x of minus t will give you double xe of t, and if you subtract, you get 2x of t. Then if I give you a signal x of t, then you take the signal, you add to it x of minus t, and this is called the time reversed signal. And if you have a formula for the signal, you just take its its function of t, and you replace each t by minus t. So if you take x of t plus x of minus t and then divide by 2, you will get a signal that is even, and this will be the even component of x of t. And if you subtract, you will get basically the odd component of x of t. So sometimes in some problems, it is useful, it is convenient to basically do this type of decomposition. Take a signal, and rather than basically dealing with the signal directly, is to decompose it into two parts, one of them even and the other odd. Sometimes it's useful, sometimes it's not. Okay, but it is something that may be useful in some problems. Now, if your signal is even and you are integrating it over a symmetric interval from minus L to L, okay, and if it's even, so basically the signal is, again, it's symmetric. It looks something like this. So if you want to integrate it from minus some finite number to some finite number, well, what you can do is that you can just integrate it from 0 to L, right, and then multiply by 2. Okay, sometimes this may be a bit more convenient than just doing the integration from minus L to L. So if you are integrating, again, an even signal, and your integration is from minus 7 to 7, or from minus 20 to 20, then you can just integrate from 0 to L, or 0, whatever L is, some finite number, and then you can multiply by 2. Okay, so this, again, can be like to exploit the even property, like, sort of to simplify, an integration. If we are talking about a sequence, then again, if you have a sequence and you are summing from minus big M to big M, so this sequence is x of 0. So there is a term corresponding to n equals 0. Then there is x of 1 plus x of 2, all the way up to x of big M. And then, of course, there are, when the index is minus 1, we have x of minus 1, we have x of minus 2, and so on. Okay. Now, so this is the summation. It is a summation from small n equals minus big M to big M. So what you can do is that you can say, okay, x of 0 is alone here. So this is x of 0. And then if your signal is an even signal, then x of minus 1 is equal to x of 1. So these two guys, for an even signal, these two guys are the same. X of minus 2 is equal to x of 2. These two guys are the same, and so on and so forth. So rather than summing from minus big M to big M, again, it may be useful in some, problems just to do a summation from 1 to big M. Okay, so you are summing like x1, x2 till x of big M, and then multiply by 2, and then add this x of 0. Again, another form that may be useful. Now, if your signal is odd, then again, if you are integrating the signal from minus L to L, so assume that you are integrating this signal here from minus L to L. So you are computing basically the area, like this area, because the signal is odd, and because of the convention used that basically if your curve is below the horizontal axis, then basically its integral is negative. Then if you integrate from minus L to 0, you will get a negative result that is exactly equal to the integral from 0 to L. And so basically the full integral from minus L to L will be some number plus its negative, and so you will get 0. And so this is really useful. So, but for even signals, you are left with an integral to do. You still need to do this integration from 0 to L. If your x of t is odd, or if your sequence x is an odd sequence or odd discrete time signal, then the integral from minus L to L, or the summation from minus big M to M, this will give you 0. And if you can spot something and you recognize that it is odd, and then you are integrating or summing it from, again, in a symmetric fashion from minus big M to big M or from minus L to big N, then, this will be 0. And again, this can save you, rather than doing this integral and then to discover, at the end after doing, several lines that basically it is 0. If you can discover, that, this signal, this signal has a symmetry, it's an odd signal. So if it's an odd signal, you can just, enjoy these basically properties here. Okay. So, there are useful signals, and I'm sure that actually them. But the idea is that sometimes those signals, or some of them, not all of them, are defined differently in different courses. And so let's basically let's try to be on the same page, so that when I write down these things later, we basically have the same understanding of what these signals are. So the rectangular pulse, okay, so I will write it like this. So it is A rect T over big T. So this outside guy is the amplitude. This signal has a compact support, and it is an even signal. It is an even signal, and its amplitude is A from minus big T over 2 to big T over 2. Otherwise, it is 0. Of course, the signal is discontinuous at minus big T over 2 and big T over 2. This is a rectangular pulse. It does not repeat, so it is an aperiodic signal. And, this signal, of course, it's integrable. Its magnitude is integrable. Its energy is finite. It is an L1 signal. It is an L2 signal, and so forth. Okay, so this is the rectangular pulse. And again, I will write it rect. So anything outside will be the amplitude. Okay. So T over big T, then basically, so from big T here, so let's say that it is rect T over, let's say 6. Then when you see something like this, you know that it is a rectangular pulse, right, going from minus 3 to 3. And if there is a 1 outside, then its amplitude is 1. Okay, so let's agree on this for the definition of the rectangular pulse. Also useful is a triangular pulse, okay, and so I will write it like A. So A again is the amplitude, and then try A over big T. Here there is again maybe sort of confusing, but in the definition here, basically for the try, if I have A, sorry, this should be small t. This is a small t. That's an error. So A try small t over big T. Okay. Now the triangular pulse goes from minus big T to big T. Okay. So if I tell you try, let's repeat this one here. Try T over 6. Okay. So this one, it will not go from minus 3 to 3 like here. It will go from minus 6 and then 6. It will go up to an amplitude, if there is a 1 here, to 1, and then it will go like this. So it is linear with a positive slope here, and then with the negative slope. And again, I emphasize that, but basically the notation I'm using here is that if it's triangular function, triangular pulse, then it is from minus big T to big T. And if it's rectangular, it's from minus big T over 2 to big T over 2. Again, it's an even signal. It's L1, L2, and, you can compute its energy. And here, for example, I'm computing the energy basically using the, since this is an even function, so you can see here, basically if you want to compute the energy, you should integrate from minus big T to big T. But because this is an even function, and if you square it to compute the energy, you will get an even function, then you can just do the integral from 0 to big T, and you multiply by 2. Okay. So those are very important. They appear a lot again, in several contexts, including in Fourier analysis. Sinc function. Okay, so we so sinc function, it appeared in when we did basically the power of a sum of sinusoids. So actually, that's now let's talk about this in more detail. Because it's a bit tricky. It's trickier than those guys. Those guys, they have a compact support. Rectangular pulse is non-zero only from minus big T over 2 to big T over 2. Triangular pulse is non-zero only from minus big T to big T, but this guy is living forever. And the sinc, there are people defining sinc T as sine T over T. Okay, but this is not the definition we are using here. We will use the definition sine pi t over pi t. So if you have used in a previous life, if you use the sink of t as sine t over t, so again, you know, no, I mean, we will not use this here. Every problem will assume that this is the definition of the sink function. Sink of t is sine pi t over pi t. Okay, so let's agree on this one. Everything we'll see, especially in Fourier analysis, will assume that this is the definition of the sink function. Now, if you look at the sink function, you see that there is a problem, and the problem is that you are dividing by t, and what if t is equal to 0? So definitely 0 should be excluded from the domain. However, the nice thing is that, you know, if you take the limit as t goes to 0, you'll find that the limit is equal to 1. And so what you can do is that you can just define, you can say, okay, the function, its value at 0, I will take it to be the limit, and it is equal to 1. Okay, so sink of 0 is like sort of, by definition, we will take it to be the limit as x goes to 0 of sine pi x over pi x, something like you can easily do using L'Hopital or something, and you will get a 1. And so this will be a 1 here. Okay, again, so when I write sink of t or sine pi t over pi t, automatically, so I do not need to say it every time, automatically I mean that for t equals 0, we do not divide by 0 or anything. We just define the function as 1. Okay, so if you want like to be very, you know, sink of t is equal to 1 if t is equal to 0. If t is not equal to 0, it is sine pi t over pi t. So if you want to be like extremely careful, you will write it something like this. But in this course, we'll just, you know, understand that when I write a sink, I mean this one, but you know, but I will just write the second line here, and we know what it looks like at t equals 0. The sink function is aperiodic. Okay, so it has this sign, but it is divided, you know, sine pi t, but it is divided by t, and so it will decay, and so it does not repeat itself. It is an aperiodic signal. It is an even signal, so sink minus t is equal to sink of t. And the reason it's an even signal is that the sine function is an odd function, and the linear function here, t, is an odd function, and basically an odd over odd function. This will give you basically an even function. Now, what about basically, let's, you know, the part that we used in the proof of the power of the sum of sinusoids. Okay, so basically we have a decay towards 0. So we have this property which I used in the previous slide, and to show this, okay, so what is limit t tends to infinity of sine pi t over pi t? Okay, so how can we evaluate this limit? So what you can do is that you can basically take limit t tends to infinity 1 over t, and then we have sine pi t. Okay, and so there is a rule for limits, which is that if you have a bounded function, and the sine function, it's oscillating, but it is bounded, right? Because the sine itself, it's between -1 and 1. So if you have a bounded function and it's multiplied by something that goes to 0 as t goes to infinity here, okay, then actually the whole thing goes to 0. Okay, and you can actually show this rigorously, but you know, again, it's again basically it's like generally if you have a function that goes to 0 and multiplied by a bounded function, you know, so this guy alone, it does not have a limit, right? Because the sign is oscillating, but it is bounded. And if it's multiplied by something that we are sure goes to 0 as t goes to infinity, then the overall limit will be 0. And the same if we take the limit as t goes to minus infinity. So this thing is decayed actually, and it goes to 0 on both sides. The reason I prefer the definition of the sink with a pi is that once you have the pi in the definition of the sink, then sink of an integer becomes basically two cases. If the integer is 0, the sink is equal to 1, whereas the sink of a non-zero integer will exactly be equal to 0. And the reason is that if sink m will be sine pi m over pi m, and so if m is a non-zero integer, we have a non-zero number in the denominator, and we have sine pi m in the numerator, and sine pi m, where m is an integer, is equal to 0. Okay, and so basically this definition of the sinc function, it will make the sinc function 0 again at all non-zero integer multiples, at all non-zero integers. Okay, if basically if you are not having this pi, it will be at all non-zero integer multiples of pi. Okay, but again, in this course, we will stick to this definition here. And so sinc of an integer that is not 0 is exactly equal to 0. Okay? Now, is this function integrable? Is it absolute integrable? Is it square integrable? Okay, so this was basically question 4 in homework 2. Basically, the function itself is integrable. So if you do not put an absolute value or anything, the function isn't. So you proved in problem 4a in homework 2 that basically we have this result here. And so to integrate the sinc, we can integrate the sinc from -infinity to infinity. Right? The sinc is an even function, and because it's an even function, then its integral from -infinity to infinity is double its integral from 0 to infinity. And very easily you can do like a change substitution, replace pi t by u, so that you can make use of the result in the homework, and you will discover that the integral of the sinc function, as defined in our course, if you integrate it from -infinity to infinity, you will get a 1. You will get exactly 1. Okay, so this is basically it is an integrable continuous time signal. Okay, so before proceeding, let me comment on something. I haven't basically graded all of your homework submissions. But the submissions that I have seen, basically I found almost for everyone basically some mistake or some problem in basically doing this problem properly and in applying Fubini. Okay, so let me just take a couple of minutes and talk about this, because this is important. And if you have a misconception, I mean, it's time basically to clear this. So the problem tells you basically that we want to take the limit as alpha goes to infinity, 0 to alpha sine, let's say u over u d. Okay, this basically integrals. If you learn the theory of integrals, you start first by integrating over some finite interval from a to b. Now, to push an integration to infinity, this is not actually the original integration. This is called an improper integral, and it is defined as a limit, right? So basically, if I write integration from 0 to infinity, I simply mean some complicated procedure. I mean that you have an upper limit of integration that is finite. You go and evaluate this integration for all possible values of this upper limit, and then you do this limit as alpha goes to infinity. If this limit, it may not exist. If it exists, then this guy is well defined. Okay, so again, this is actually, so integration, here we will liberally do the integration from 0 to infinity. We will not like do it this case, to save time, we will just, do things like typically done in engineering. We will do like integration by parts, and then we put infinity and so on. But the correct way of doing it is just like in the problem statement. You should have an upper bound, evaluate your integration and get it in terms of this upper bound, and then go evaluate the limit. Okay, so this is what the problem is about. So you should integrate from 0 to alpha. And now to do the integration, I gave a hint in the problem. I remember the hint was basically that I will take this 1 over u and write this as sine u, and 1 over u I wrote it as basically the integral 0 to infinity minus eut dt du, so that when you integrate this guy here with respect to t, you will get 1 over u, right? Now you have a double integral, and you need to justify basically whether you can do the integration first with respect to u, right? Because if you do the integration first with respect to t, you will get this guy here and you are stuck. I mean, how do we handle sine u over u? So it may be useful actually to do the integration first with respect to the sine, with respect to u, but you need to justify, because according to this, you should first do with respect to t to get this 1 over u, and then do with respect to u. But how can we deal with sine u over u? It does not seem to be something that is tractable, and so the idea is to do with respect to u first, but then you need to justify, because basically interchanging the order in a double integral is not always guaranteed to give you the same result. So we need to justify. So we need something like Fubini. We use Tonelli if our stuff is real valued and non-negative, but this will not work here because we have the sine function. And the sine function is, it's positive and negative. So Tonelli will not help us. So we need Fubini. So for Fubini, we need a check. And the check is on the magnitude. So we need to check that. The integral from 0 to alpha, the magnitude of sine u, and then integral from 0 to infinity, sine u, magnitude sine u, and then e to the iut dt du. This guy is real valued and non-negative, so we do not need to put an absolute value there, du. We need to check that this guy is finite. So the check, what I saw in some solutions is that people are the check without the absolute value, without the so generally, I mean, you can have complex valued functions. You should take their magnitude and then show that basically the double integral of the magnitude is a finite number. If it is, then you can go back to your original integration without the magnitude, and then you can do the interchange. Okay, and when you do the check, you do not need to worry about the order of your operations, because by Tonelli, once you take the magnitude, your integrand becomes real valued and non-negative. So you can take any order of your choice. You can do it in any order of your choice. Okay, so you need to check this, and basically, if you check, some people did this, but the check, they replaced the alpha by infinity, and I do not see actually how it can be justified. Actually, you will need a finite alpha for Fubini to work. Okay, I will upload the solutions shortly, and please, review this part again, because I found it, let's put it this way. All the solutions I have basically opened, no one basically did this part like in a course. There's some mistake here or there. Okay, so let's basically try to learn how to do these things carefully. Okay, Fubini means a check using the magnitude. Okay, so you need to, if you find the sine function is not non-negative. It can be negative, so you need to replace it by its absolute value. And now for the integral itself with alpha. Okay. Is Fubini, and like something. What is the other? This dominated convergence theorem and so on. They are sufficient. They are sufficient. They are not necessary. Okay, they are sufficient conditions for basically the validity of the interchange, but they are not necessary. They are sufficient, not necessary. Okay. So let's go back here. So the function is integrable, and again, its integration is basically problem 4e. You can just, basically 4e is about sine t over t. Here we have sine pi t over pi t. Using this substitution, you can easily get that the required result is 1. It is an L2, so basically it is an L2 signal, because if it is square integrable, and so this will start 4b, okay. And so again, you can just do this substitution and get that also the integral of sinc square is equal to 1. But it is not absolute integral. It is not L1. So this function is L2 but not L1. And so for in problem 4c, basically you showed that the integral of the magnitude is infinity. It's a plus infinity. Okay, so it is not L1. It is L2. It has finite energy. So this guy is actually it's an energy signal. it has a finite L to norm, finite energy, but it is not absolute integrable. It is integrable, but not absolute integrable. Okay, and let's go to another useful signal or function, the sine function. So this is an odd function that is defined as such. Sine of t, there is a missing n here, so it's sine here. So it is 1 if t is positive, minus 1 if t is less than 0, if t is negative, and 0 if t is equal to 0. Okay, and so it is an odd signal. It is odd. It is aperiodic. It is a power signal. You know, if you compute its energy, if you compute the energy, you will square it, and when you square it, you will get basically 1 over the whole set of real numbers except at 0, and then so the integration will be infinity. But you can compute the average power. So basically, when you square the signal, it will be like this. Okay, the 1 squared, which is 1. And when you integrate it, it will be from minus L to L. That's 2L. And in the definition of the average power, you divide by 2L. So this will give you 1. And the limit of 1 as L goes to infinity is just 1. So it is a signal that it is a power signal, and its average power is exactly equal to 1. Okay, and of course, you know, I do not need to mention that basically the fact that it is 0, at a single point, which is equal to 0, is something that is irrelevant to integrals, right? Integrals are applied to things happening on sets of measure 0. So the fact that, you know, we don't have 1 at t equals 0, the function is 0, is nothing from the point of view of an integral, right? Because, you know, a point is a set of measure 0. And so basically integrals do not care about this. Okay, so that's the reason here I just wrote integral from minus L to L1 squared. Okay, and I wrote it because, you know, what about this line here? You know, it's a non-issue. It's a non-issue because integrals are insensitive to basically, things happening on a set of measure 0. The signal is not absolute integrable. It's not square integrable, again, because when you take the absolute value, you make it equal to 1 almost everywhere, and so basically the integration will give you infinity. The Heaviside unit step function, very important, and it is the function that is 1 when t is positive, 0 when t is negative. And, you know, what about when t is equal to 0? Some people define it to be 0 when t is equal to 0. Some people define it to be 1. Some people define it to be 1 over 2. Here, it's like I don't care. You can put at u of 0 to be anything. You know, it won't matter. So, again, we will look for the continuous time unit step function. Okay, the value at t equals 0 is not important, and the most important thing is that the function is 1 when t is positive, is 0 when t is negative. And here is its plot if we choose u of 0 to be equal to 1, and of course it's discontinuous at the origin at t equals 0. It does not have symmetry, so the sine function, it's an odd signal, but the unit step function, it's neither odd nor even. It's aperiodic. It's a power signal, so you can use basically the same argument above. The energy is infinity, but the power, you can show that it is equal to 1/2. And what is the relationship between the sine function and the Heaviside unit step function? So ignoring t equals 0, okay, so if t is not equal to 0, how can you get this from that? If you take 2u of t, right, so t is not equal to 0, 2u of t, so you multiply u of t by 2, so it will be, rather than 0, 1, it will be 0, 2, and then you subtract 1. So this is like sine t. Okay. And this relationship between the sine function and the Heaviside unit step function is important, is important in Fourier analysis. Okay, so again, these two functions are not far from one another. So basically, you can look at it the other way, that if you take the sine function, sine of t, if you add a 1, then you push it, basically this minus 1 becomes a 0, this 1 becomes a 2, and then if you multiply by 1/2, you get u of t. Okay, so basically these two guys are related, and again, this relation can be useful in obtaining some Fourier transforms, as we will see later. The discrete time unit step function. So this is the discrete time. So that's a sequence. That's a discrete time sequence. Now for this one, you don't have a choice. U of 0 is equal to 1. Oh, I actually wrote it. I wrote it 1. Okay, so very bad. Okay, it is 1. It must be 1 at 0. Okay, so for the discrete time unit step function, so if we are talking about the discrete time version of the unit step function, okay, then this should be U of 0 is exactly equal to 1. For the continuous time case, we don't really care, and you can put it any way of your choice and you will get the exact same results. For the discrete time case, no, U of 0 is equal to 1. Okay, so U of n is 1 if n is 0 or positive, and U of n is equal to 0. In the discrete case, no, it is 1 at n equals 0, 1 at n equals 1, 1 at n equals 2, 1 at n equals 3, and so on. So basically, the slides I sent you, this guy was missing. Okay, it is equal to 1 at n equals 0. Okay, so this is actually, it's correct. No, it is 1. It is 1. I emphasize it is 1. Okay, it must be 1. Right? Again, these things will matter, like when you compute for discrete time signals, when you compute the discrete time Fourier transform and so on, these things will, it's different, So, so basically, yeah, this one, it's defined to be 1 at n equals 0. It is power signal. It is L2. In the piece one, oh, yeah. Okay. Okay. Yes, I see it now. Less than or equal to 0. Yes. This is true. Okay, so this is 0 when n is less than or equal to 0. Okay. The discrete time delta is a very simple sequence. No, because this is a discrete time sequence, so it is like sort of defined on the set of integers. It is undefined elsewhere. Okay, so this is general for discrete time signals. When I say x of n, basically I'm defining it on the integers. And if you ask, what is x of 1.5? It is not 0. X of 1.5 is not defined because it's basically defined just on the grid of integers. Okay. So that's the reason we draw it like this. Between 0 and 1, between 1 and 2, between 2 and 3, it is not there. Okay. The discrete time delta is a very simple sequence. It's a sequence that is 0, 0, 0, 0, 0, and then it is 1 at 0, and then it goes back to zeros again. It is just equal to 1 when n is equal to 0. Otherwise, it is equal to 0. So that's the discrete time delta. It is not something to be afraid of. It is, it's a very like sort of a standard or classical discrete time sequence. Okay, so it is just 0, 0, 0, and then there is a 1, 0, 0, 0, and this happens only when n is equal to 0. Okay, so this is the discrete time delta. But the continuous version, the continuous time version, the Dirac delta, delta of t, that's a monster because it is not actually a function. Okay, it is in math that is called either a generalized function or a distribution. It is something that, again, we will not deal with it in a very rigorous way. But I will, maybe I will dedicate like half a lecture or something on how delta t is actually, it emerges in a rigorous way. But most likely, we deal with the Dirac delta as a monster, basically, that if you, with what you can say, some rules of engagement. So we'll agree on a certain set of rules that you follow, and if you do this, you will not do a mistake. You will get your results correctly. So the Dirac delta again is not actually a function, and I deliberately avoided using it. You will see that I just keep it the Dirac delta and I stop, because if you call it function, that's actually wrong. It is not a function. It is a generalized function. or a distribution, and it behaves in indirect ways. Okay, again, maybe I will dedicate half a lecture or something on it, but like I think maybe in the next lecture we will agree about how to basically deal with it. Okay, so the delta of t is coming soon, but the discrete time version is like, you know, it's a very ordinary sequence of numbers, you know, just 1 at n equals 0. Okay, but this guy is, you know, is something that we need to be careful about, which turns out to be extremely important in physics, extremely important in engineering, and so on. And basically this thing was invented outside mathematics, okay, and it took a while for mathematicians to make it basically rigorous. So it was invented by Dirac, physicist Dirac, and then it was made rigorous by French mathematician Laurent Schwartz, and actually he won the Fields Medal because he basically made the theory of Dirac delta basically rigorous, okay. Single signal operations, you know, I will not like spend much time on this. So signals, you know, we do like simple things to signals that are like, you know, they typically appear in also the, you know, the math of Fourier analysis. You know, so suppose that this is your signal x of t, so that's signal x of t, and I want like this signal x of minus 3 t plus 9. Okay, so this is like a classical signals and system thing, and you know, you may have encountered it or like with very high probability in a previous course on signals and systems or whatever. And basically, to understand something like what is x of minus 3t plus 9, we have actually three simple operations. So let's do them one by one. So if you have a signal x of t, so this is our signal x of t, so it is basically linear here, and it is linear there, and then otherwise it is equal to 0. Then the first simple operation is basically the so-called time reversal. You can call it mirroring or reflection, or whatever you want to call it. You take x of t and convert it into x of minus t. Okay, and so what happens here is that you basically reflect your signal about the vertical axis. So if this is what the signal looks like, then x of minus t, then basically this part here at minus 3 and 0, it will go there to the positive side, and the part on the positive side will go to the negative side. So it is reflection, it is mirroring, it is time reversal, you call it whatever you want to call it. Okay? Now, for continuous time signals, there is something else, that time scaling. And it is very important to use the word time here, time scaling, because you can scale a signal, you can scale the amplitude of the signal. So scaling the amplitude of the signal is like to multiply the signal by 5 or minus 17 or something like this. But here we are talking about time scaling, and time scaling means that you take a signal of time, let's say g of t, and then you make it g of 2t, or g of t divided by 2, something like this. Okay. So so like here, if we do time scaling, okay, let me, so this signal will be x of, so this guy is g of t. Here what I'm doing is g of 3t. Okay, generally speaking, we have g of alpha t, okay, and when we do the scaling, so this is the time scaling, we take alpha, you know, alpha. Of course, if alpha is 1, it's a trivial, because if you scale alpha is 1, then it's your signal back. So the important regions are basically if alpha is between 0 and 1, and if alpha is greater than 1. Okay. So if alpha is greater than 1, like here we have g of 3t, we are basically compressing the signal. So this is compression. So we compress the signal by this factor of 3. So if the signal here is like, so here it, on this part, it extends to 3, 0. Now if you compress it, you basically, you make it go to 1, 0, rather than 3, 0. And on the other side, it extends here to -3 and 2. This -3 now becomes -1 because again you are compressing the signal with a time scaling factor of 3. It's not shown here, but if alpha is less than 1, then you are doing basically stretching. You are stretching your signal. Okay, so you can basically, so time scaling means that you take your signal, you do not manipulate the amplitudes, you simply, it's sort of, the intuitive way of thinking about it is that you stretch or you compress your signals. And there will be like a nice discussion in this course about basically the relation, what happens to the Fourier transform of the signal when you scale it, and we will try to relate this to something in Fourier analysis called the uncertainty principle. Okay, so yeah, I mean, because like when you say that I'm scaling the signal, sometimes people will understand it as scale the signal by a factor of 2. It's like you multiply the amplitude of the signal by 2, right? So if you just say scaling, it's typically if you just say it, most likely people will understand it to be amplitude scaling, in which like you amplify the signal or you attenuate it by multiplying. So it is like you multiply the vertical axis, okay? So the amplitude. But here I'm talking about time scaling, and it is basically recommended that when you mean time scaling to just say time scaling and not just the word scaling, okay? So it is something related to the horizontal axis of time, okay? And basically you can shift the signal. You can move the signal to the left and to the right. Okay, and so we have like x of t minus 2. So if this is your x of t, okay, and it is centered here around 0, then x of t minus 2 will look something like, it will be centered about 2. So this will be a shift to the right, while if you have x of t plus 2, then it will be a shift to the left, like this, around minus 2. Okay, so this is, okay, so you can basically shift your signal. And again, those shifts are very important in Fourier analysis. Let's go back to our example. So x of t actually here, again, it's like the conventional signals and systems problem, plot x of minus 3t plus 9. So typically the way I do this is I write this thing here as x of, then I try to have an inner bracket with t and the shift, okay? So t here is multiplied by minus 3, so I will pull minus 3 as a common factor, so that I just have a t here, and then, to get the correct result, this will be minus 3t, but we have a plus 9, so we need to have a minus 3, okay? So this is the first thing. And then, if you have a minus sign here, then you start by doing reversal, okay? So this is what I did here, so you do the mirroring or time reversal. If there is not a minus sign, then you skip this. You do not need to mirror or do anything. If there is a minus sign, you do reversal or not. Then you do the scaling. You do the times. I should say time scaling. You do the time scaling. Again, if this factor is greater than 1, you compress your signal. If it's less than 1, then you stretch your signal. And then finally, you do your basically shift, time shift. Okay, and here, because we have t minus 3, then we shift to the right. So basically, this signal here, it is like here we have at 0. Then now this guy will become at the point, at 3. Okay, because of the shift. Okay, and so like a clean, this is a clean plot of x of minus 3t plus 9. I think. You cannot do these operations in any arbitrary order. If you do, so I think this one is correct. If you do the time reversal followed by time scaling followed by time shift, there may be orders that are actually wrong, will give you the wrong result. Okay, but so take care. That sometimes if you do things assuming that you can do these operations in any order, no, they are not the same. Okay, so basically the order that, this is one order that gives you things correctly, that you do the time reversal first, then the time scaling, and finally you do the shift. Do whatever you want. I'm sure that you have your own method, but just make sure that you do things correctly. Now, for a discrete time signal, we can shift a discrete time signal. We can time reverse it, right? So this appears to be like a sort of like straightforward extension to what we have for continuous time signals. But what about time scaling? I mean, how can we stretch or compress a discrete time signal? Okay, so see what I'm saying, that if you have a signal that looks like this, so it's defined just on the integers. Let's say it looks like this: 3, 2, 1, 0, 0, 0, 0, 0, and so on. So that's x of n. What does it mean that we stretch it? Now, stretching for a continuous time signal or compression makes sense because like t is a real number, the parameter is a real number, but n, discrete time signals are basically defined only on the integers. And if we do an operation on them, we should basically get discrete time signals, new discrete time signals that are also defined on the integers. So what is time scaling for discrete time signals? Okay, so again, yes, adding zeros. Yeah, exactly. So it is called upsampling and downsampling. Upsampling and downsampling. So basically, it is something that it's the sort of the conceptual difference between basically the simple operations. For time reversal, it's the same thing for continuous time, discrete time. For shifts to the right and to the left, I mean, you can shift. Of course, the shifts for discrete time signal are only integer shifts. So you can have x of n minus 3. This is okay. X of n plus 7. This is okay. X of n plus 0.5. Wrong. This is not correct. So again, when you shift for a discrete time signal, you should basically have n minus an integer or n plus an integer. For time scaling, the concept is basically like fundamentally different. Again, because we are talking now about sequences that are defined just on the integers. Okay, so let's see basically how these things are defined for a discrete time signal. So we have upsampling. Okay, so upsampling, and if you see the block diagram of a discrete time system, then this is indicated by a box with an up arrow, and then this parameter L, and so L is an integer. L is greater than or equal to 2. Okay, and this is called the upsampler, and basically this is a discrete time system or discrete time operation in the sense that the input to this block is a discrete time signal, and the output is another discrete time signal. And the output y of n, if you want to express the relationship mathematically, it is basically defined as such. It is x of n over L. It is x of n over L, right? But you cannot do this for a discrete time signal, right? Unless this thing is an integer. Remember, discrete time signals are not defined, at 1.5 or 7.8 or something like this. You need this guy to be an integer. So y of n is equal to x of n over big L if L divides n. If n is a multiple of L, or basically if n is divisible by L. Otherwise, y of n is equal to 0. Okay, so this is the definition of the upsampling operation. Okay, it is y of n is equal to x of n over L so long as n is a multiple, an integer multiple of big L, and big L is the parameter of the upsampler. It's an integer that is 2 or more. If n is not a multiple of big L, then basically u of n is exactly equal to 0. So let's take an example. So this is x of n, and this is the sequence, and this notation for discrete time signals, basically it is the samples of the sequence, and there will be an up arrow here. This is different from this up arrow. This up arrow in x of n, it means that basically this is n equals 0. this is n equals 1, this is n equals 2, and this is n equals 3. So this is like to tell you that, because if you have just a sequence of numbers, then where is the origin? So basically this arrow here is to indicate what is the origin of your discrete time for your basically n axis, okay? So if this is x of n and l is equal to 3, let's first try to use the formula, and then we will discover that actually that the operation is simpler than this. So the formula may suggest that something very complicated is happening, but actually it is very simple. So what is y of minus 3? What is y of minus 3? Then again, according to the rule, this will be x of minus 3 over 3. I will take here as an example, L is equal to 3. So minus 3 is divisible by 3, and the result is minus 1, which is an integer, fine. And what is x of, so this is minus 1, this is minus 1. When x of minus 1 is equal to minus 11. So basically this is what we have here. What is y of minus 2? So y of minus 2, n is minus 2. Now minus 2 is not divisible by l, which is equal to 3. Then y of minus 2 is 0. Minus 1 is not divisible by 3. So y of minus 1 is 0. Y of 0 is x of 0 over l, which is x of 0. So this is 1. Y of 1, 1 is not divisible by 3. So this is 0. 2 is not divisible by 3. So this is 0. Y of 3, now 3 is divisible by 3. So y of 3 is equal to x of 3 over 3, which is x of 1. And you can read it from here, x of 1 is equal to 2. What about y of 4? 4 is not divisible by 3, that's 0. 5 is not divisible by 3, that's 0. Y of 6, 6 is divisible by 3. So this is x of 2, which is equal to 3 according to this sequence. This is x of 2, it will be y of 6. Okay? So this is x of n. Now let's collect those results here and write down our new sequence, y of n. This is our new sequence, y of 0. So this is y of 0, this is y of 1, this is y of 1, this is y of 2, 3, 4, and so on. And you will discover that what happened, if you compare the sequences, that basically when we did this operation here, upsampling by factor L is equal to 3, what we did is that we inserted 2 zeros between each 2 successive samples. Okay, so it's always the case that x of 0 and y of 0 are equal. So x of 0 is always equal to y of 0. Okay, or y of 0 is always equal to x of 0. And then basically this expression here, you know, the expression that we have here, again, it just tells you go to the sequence that you have and insert big L minus 1 zeros between each 2 successive samples from signal X. So this is the upsampling operation. 0 insertion. And specifically, you insert L minus 1 zeros between each 2 successive samples so that you get your new sequence, which is Y. Okay, so this is basically the upsampling operation. Okay, it's like stretching, but again, the question is how do you stretch? So now it's like you add zeros. Okay, now those zeros are rings. So now this signal Y, it has those zeros. Samples of zeros count, you know, they are important, you know, they have an effect when you basically study something like, you know, the Z transform of the signal, the Fourier transform of the signal, and so on and so forth. Okay? Downsampling, it is a building block denoted by a down arrow, and then also M is an integer, and M is greater than or equal to 2. Okay, so it is also a discrete time operation, discrete time block. Its input, it is a discrete time signal. Its output is another discrete time signal. And now the formula is basically y of n is equal to x of big M times small n. Okay, so again, better to see this in operation with an example. So x of n is, let's have the sequence here. Let's choose m to be equal to 2. So y of 0 is equal, so y of 0 is equal to x of 2 times 0, which is 0. And so this is always the case. Whether you are doing upsampling or downsampling, it's always the case that the output evaluated at 0 is the input evaluated at 0. But then, what is y of 1? What is y of 1? According to this rule, it is x of, so it is x of m times 1. And m in our case here is 2, so this will be x of 2. So this is x of 1. This will be x of 2. So it is 30. Yeah. Speak, please. Yeah. Okay. So basically this will be 13. Then y of 2 will be x of 4 because it is x of, again, we multiply the index n by big M as we have here. And so this will be x of 4. Where is x of 4? This is 0, 1, 2. This is x of 3. This is x of 4. So this is 19 and so forth. Okay. Now for negative y, what is y of minus 1? It will be y of minus 1 times 2. So it's x of minus 2. Where is this guy? So this is x of minus 1. This is x of minus 2. So it is equal to 3. And so on and so forth. So this, if you just blindly apply the basically the formula. Okay. So it is like, you know, the operation of compression. But now let's see actually what, you know, if we want to do this with discrete time signals, what is y? So here is y. So you apply the formula, you will discover that basically y of 0 is this 7. This is y of 1. This is y of 2. This is y of minus 1, and so on and so forth. And if you compare this y with x, you will find what? We keep 7, discard 11. Keep 13, discard 17. Keep 19, discard the other signal. It's like when m is equal to 2, we keep every other sample. We keep a sample, discard the sample. Keep a sample, discard the sample, and so on. Okay, so downsampling again is described by this mathematical expression. And you know, if you want to describe it in words, is for a downsampler with a factor of big M, what you do is that you only keep the samples at the integer multiples of big M, and then you discard the rest. Okay, so you take the sample, you take x of 0, then you discard big M minus 1 samples, then you take x of big M, then you discard M minus 1 samples, then you take x of 2 big M, and you do the same on the negative side. Okay, so you can describe this in words as keeping the samples at the integer multiples of big M, while the others simply disappear. They are completely removed from the sequence. Okay, so we get an effect that looks like this. Okay, so the last thing that I say that is like these operations like seem like pointless. I mean, what's the benefit of something like this? You know, so you basically have this, you know, you have a sequence, you simply discard samples, or in the previous case, you insert zeros. I mean, what is the point? Okay, so it turns out that all modern digital signal processing systems actually rely on these two operations. These two operations, yes, they appear to be useless when you consider them alone, but the upsamplers and downsamplers, if you combine them with digital filters, then you design basically digital components called interpolators and decimators. And those are extremely important in modern digital signal processing. So do not basically, you know, look down at those things, you know that you think that those are basically like useless operations. They may look so, but in fact, you know, they are very important when they are coupled with other digital components like a digital filter. A well-designed low-pass digital filter with an upsampler or downsampler, you can do wonders with it. You know, specifically in, you know, systems that are called the multi-rate. Is upsampling an invertible operation and downsampling is not? Yes, that's true, because in downsampling you discard the samples, but here for the upsampler, you just have those zeros. You can just remove the zeros. You are back to your original signal. Okay, but for when you discard the samples, then you get back your signal.